To reinforce the microstrip analysis equations, I'm just going to do an example for you. In this example, we want to determine the characteristic impedance, the propagation velocity, and the guide wavelength for a microstrip transmission line that's 2.2 millimeters wide on a substrate that is 1 millimeter thick with a effective relative permittivity, electric permittivity of 4.5. The signal frequency is 100 megahertz, so you can kind of visualize in your head, we've got a substrate material. It is 1 millimeter in width, and it's got a ground plane, and then on top of that it's got a signal strip, and that is 2.2 millimeters. The relative permittivity of this material is 4.5, and the signal that's on the signal line has a frequency of 100 megahertz. So if we were to kind of try to visualize what's being said here, this is the situation that we have. So we can just extract some information. W, the width of the trace, is 2.2 millimeters, and H is equal to 1 millimeter. So W divided by H is equal to 2.2 millimeters divided by 1 millimeter is equal to 2.2. So W to H is greater than 1. So if we're to flip back to our analysis rules, we see that it is greater than 1. So we are in the low impedance regime, and we're going to use this equation right here. So just say therefore low impedance. The characteristic impedance equation, I'm just going to write it all out here. It's 120 pi divided by the square root of the effective electric permittivity for that material times the W to H ratio plus 1.393 plus 2/3 times the natural log of the W to H ratio plus 1.444. So all of this is in this parenthesis here. Square root of epsilon effective multiplies by all of that. We need to calculate the effective electric permittivity here, so that's the formula for that is the permittivity of the actual substrate plus 1 divided by 2 plus epsilon r minus 1 over 2 times the square root of 1 plus 12. In here, this is the H to W ratio. I've seen a lot of people get that mixed up, so be careful that you notice that that's H to W, not W to H. So that's going to be the 4.5 plus 1 divided by 2 plus 4.5 minus 1 divided by 2 times the square root of 1 plus 12 times 1 divided by 2.2. And normally I have to include units in those of millimeters, but of length in there, but they're both millimeters, so they'll cancel out in this particular instance. This gives us an effective electric permittivity of 3.43. So now I've got everything I need to calculate Z0. Z0 is going to be 120 pi times the square root of 3.43 times 2.2, right, that's the W to H ratio that I calculated right here, plus 1.393 plus 2/3 times the natural log, again the W to H ratio, so 2.2 plus 1.444. So all of that's in the denominator there, and that gives me a Z0 of 36.54 ohms. Right? I was also asked to calculate the propagation velocity. Propagation velocity is just equal to c divided by the square root of the effective electric permittivity. So that's 3 times 10 to the 8th meters per second divided by the square root of 3.43. Remember, effective electric permittivities are unitless, so that gives me 1.62 times 10 to the 8th meters per second is the propagation velocity. The last thing I was asked was to determine the guide wavelength, lambda g. So what is the wavelength of the signal in this microstrip T-line? And to do that, we just take the propagation velocity and divide it by frequency. And so that's 1.62 times 10 to the 8th divided by, this was 100 megahertz, so 100 e to the 6th, and that gives me 1.62 meters, the guide wavelength for this example.